So in class today we talked about the reaction of ozone gas going to oxygen gas. So this is ozone to oxygen. And what we're interested in is looking at what the rate expression would be. And if we see the rate expression in, we think about coefficients, we realise that the change in concentration of ozone over time is going to be related somehow to the change in concentration of O2 being produced over time. And because we're looking at the, we can look at the coefficients here, we can see that this, if we look at the reciprocal, this is how these two are going to be related. And so of course that makes it rather unusual that we're talking about a half and a third. So let's try to see where this expression could possibly come from. What we could do is we could look at this initial balanced chemical equation, and instead of thinking of 2 molecules of ozone going to 3 molecules of oxygen, we could try and rewrite this expression by saying if you just had 1 mole of ozone gas, which would produce 3 moles of oxygen gas, divided by 2, and this 2 of course came from this value over here. So this is saying that if you had 1 mole of ozone, it would produce 3/2 of oxygen, which of course, you know, we could rewrite and say, well, ozone goes to 1.5 oxygen gas, and this is still balanced, of course, because what we're saying is we had three oxygens over on this side. There were 3 of them, and over here we're saying we've got 1.5 times 2, which of course gives us 3 oxygens as well. And so now we could say, well, from a rate of production of oxygen, we could say that the change in concentration of oxygen over a certain amount of time is equal to 1.5 times the change of ozone, because we know that for every 1 ozone you're going to actually produce 1.5 times as much oxygen. So the rate at which that is being produced is going to be 1.5 times greater. And so at this point we can look at this and say, oh, so here's the rate of production, which is of course our rate expression here. And if we have this rate expression, we could say, well, at this point we know this being the case, and so from a mathematical point of view we could also represent this as change in oxygen over time equals 3/2 times the change in ozone over time. And that being the case, so now we have this sort of strange 3/2 term over here. And what we could now what we could do is to say, well, if we want to get back to a fraction type of idea, we could take this value, this 3 over here, and divide both sides by 3, both sides, and what we would end up is a third O2 divided by time equals minus a half. So what this expression now says is that if we look at this expression here, it's saying a third of the rate of oxygen utilization is equivalent to or equals minus half the rate of ozone production. And so this would be a fabulous rate expression. And so if we compare this rate expression to the one at the very top here, we'll see that this is identical. And so the reason we could just briefly look at this, we could say, well, the actual equation that we were talking about if we were to rewrite this, we would just look at the fraction of the coefficient, which is the change in ozone divided by the change in time. And of course, because this is a reactant that's decreasing in concentration over time, we put a negative sign at the beginning, and then this is going to be equivalent to the change in oxygen divided by the change in time, and it's going to be over the reciprocal of the coefficient, which is exactly the same as this expression over here. So of course it's much easier to use fractions of the coefficients of a balanced equation because that's where it all comes from. But hopefully this shows that going through this math component here and understanding that the expression using the 3/2, which comes originally from the actual chemical equation, if we go through all of it, we come out with exactly the same expressions, and so it's far easier just to use these reciprocals of the coefficients. And so this is the ultimate rate expression that we're looking for.